All right, questions on homework. 19 on, you're talking chain on the chain rule section? 19, I'll start with 19, I'll go back to the others. Oh yeah. H of t equals t plus 1 to the 2/3 times 2t squared minus 1 to the 3rd. And of course, we're being asked to find the derivative of this. So what do you see happening here? You see a product rule? That should be the part that's kind of glaring right there, is that multiplication between the two. That didn't work out the way I wanted it to. There's my separation. I have a product occurring right there. So I know that overall I have the derivative of the first one times the second one plus the derivative of the second one times the first one, and I'd be done. The issues I'm going to run into, though, are that when I take the derivative of this first one, I actually have composition there, because I have a function, t plus 1, inside of a function which is raising it to the 2/3. So I'll have to do that whole thing where I kind of cover it up and, you know, what happens. And that'll be just the derivative of this one. And then on that one, I've got the same situation. I've got a function inside of another function. Understand? Okay, so the derivative will be equal to the derivative of t plus 1 to the 2/3 times the other one, but no derivative, plus the derivative of this one times the first one, but with no derivative. Understand the notation there, the way I wrote that? Okay, now let's do this derivative right here. Would you like that as scratch work on the side, or do you want me to just do it and write it out? Scratch work or just do it? Just scratch? Who asked? You asked, right? What do you want? Scratch work? Okay. So here's my scratch work on the side. I need to find the derivative of t plus 1 to the 2/3. I need this derivative right here. So to do that, and I went back and watched a little of our video, and I was kind of disappointed because if you watch the video, it doesn't really help that I'm saying, like, cover it with your arm, and you don't really see that on the video, what I'm covering with my arm. But it seemed to work when I was in class, so I guess I'll continue that today. So I have something, right? The first thing happening is the t plus 1. Then after that, raise it to the 2/3. And that's the last thing. The outer layer of the onion here is the 2/3 power. So I have my hand to the 2/3. The derivative of my hand to the 2/3 is power rule, right? 2/3 comes out. Then my hand, which in this case was t plus 1, and then power rule, I was supposed to subtract 1 from that power. Negative 1/3. 2/3 minus 1 is negative 1/3. Now, chain rule says times the derivative of what was inside now, my hand. What is the derivative of t plus 1 with respect to t? It'd be 1, right? I don't need to write it, but I'm going to. Is that okay? Now, while I'm here doing scratch work, I may as well look at the other one. The other one was the 2t squared minus 1 to the 3rd. I can do that doing the same exact process. I can cover up the inside. So I have my hand again to the 3rd power. The derivative of my hand to the 3rd power is 3, comes out. what my hand was covering, which was the 2t squared minus 1. Reduce the power by 1, it becomes a 2. Then chain rule says go inside, take the derivative of what was in there. So what's the derivative of what was in here? 4t. Not t squared, 4t. And that turns into 12t, 2t squared minus 1 squared. That okay? Now, the derivative is equal to then that first piece we got, which was 2/3 t plus 1 to the negative 1/3 times 2t squared minus 1 cubed plus the derivative of the other one, which we got 2t squared minus 1 squared, but then times the first one without a derivative, so t plus 1 to the 2/3. I'm willing to bet a lot of money that's not what it looked like in the back of the book. How many of you actually tried to get yours to look like the back of the book? Yeah? It's a bit of a job, isn't it? That's part of what makes this a little hard, okay? Because there's a lot of algebra that can be involved in getting it to look like the back of the book. So I'm going to go through that algebra. All right, so the way that I'm looking at this is I'm going to first try and see if I can pull a GCF, like a greatest common factor, out of this thing. I notice I have a 2t squared minus 1, right, to the third power. And over here, I have a 2t squared minus 1 to the second power. Yeah? So I could pull 2 of them out from here and 2 of them out from here. I'll just do that first. So out here in the front equals, here's my GCF, 2t squared minus 1. I pulled 2 factors of it, right? So squared. Then I put a big old bracket. What was still left was the 2/3 t plus 1 to the 1/3. What did I do there? Because it was a negative exponent, I dropped it down to the bottom so it joined up with the 3 there, and here it is. And then I had pulled 2 of the factors out here, so I'm still left with 1 of those up top. Do you follow that part? This guy got dropped down. The 2 and the 3 are here. This one, I had pulled 2 of them out, which left me with 1 of them. There it is. Now over here, what do I have? Plus 12t, and then t plus 1 to the 2/3, right? Now what probably can happen next is that we can put these 2 together with a common denominator. No? Did you say no? Oh, okay. I thought maybe you're looking in the back of the book, you're like, no, that's not what they did, but I'm just doing algebra here, trying to make it look better, and eventually, hopefully, I'll get to what the book's answer looks like. So what would I have to do to get a common denominator over here? I'd have to introduce on the bottom 3 t plus 1 to the what? 1/3, and whatever I do on the bottom, I have to do the top. All right, so you see me introducing this here and here? That would leave me 2t squared minus 1 squared in brackets. I've got all this junk out here still. Nothing happened here. Now I know that these 2 are going to come together because they have the same denominator now, so I'm going to extend my division bar all the way across. I'm going to put that 3 t plus 1 to the 1/3 down here. But help me out with this. What the heck happens with all this stuff? 3 times 12, right? 3 times 12, 36. I have this t right here. What's t plus 1 to the 2/3 times t plus 1 to the 1/3? T plus 1, right? You add the exponents, 2/3 plus 1/3 is 1. So that's just t plus 1. That's actually really good. It's going to be t plus 1 up there. That t plus 1 is what happens when you put that up, not the 3. That and that together gives you this. Make sense? And I can close my bracket off. Now that was good because now I can distribute 36t through here and here. And then here I can distribute the 2 through, and then I can collect some like terms. 2t squared minus 1 squared in brackets. Let's see. I will have how many t squareds here? 4, and then how many t squareds here? 36. 36 t squareds and 4 t squareds gives me 40 t squareds. Then I have minus 2 and here plus 36t. So plus 36t minus 2 all over 3 t plus 1 to the 1/3. Am I even close to what the book's got? Still not there? Okay. I'm going to look now at what the book has just so I can see how close I am. And all I'm doing is trying to match it. What chapter is this? 2. What section is this? 5. And it's number 19, right? I would, but it includes the evens. Mm-hmm. So they got, where is it? Right here. This is where they are, right? All right. So they pulled a 2 out of this, right? Pull a 2 out of this. That 2, right? Makes that a 20t squared and a 18t and a 1. And they pulled the 3 out. So they put like a 2/3 out here. And they brought this t plus 1 to the 1/3 and they brought it back up. Again, here it is. Here's the answer. Right in there, you see it? So there's the 2/3 they pulled out. There's that t plus 1 to the 1/3 they brought it up is a negative 1/3. And then everything else we have is exactly the same. So I would say I'm there. Okay, what else? That was 19. 15. Y equals x secant kx. All right, I guess to start we need to realize that the kx is the argument of secant, so it's actually in there like that. And we also need to understand that k is a constant. X is our variable. How do I know that? Well, remember I said that there are certain letters that if they appear, we assume they're constants like A, B, C, D. X is always reserved as our variable. Y is always a variable. Z is variable. But C, K, things like that are constants, especially if it appears in here with X's. Then you assume that it's a constant. So what rule do you see here? Product rule right here. And then the derivative of x. So I'm going to have to be able to take derivative of x by itself and this, right? Derivative of x is going to be clean. Derivative of secant of kx is composition. You have kx sitting inside of secant. So you got to start with secant and then work your way in. So the derivative here is the derivative of x times secant kx plus the derivative of secant kx times x. There's your product rule. We just said derivative of x was 1 plus, now the derivative of secant kx. The derivative of secant, right, of my ID is, what's the derivative of secant of my ID, my little ID badge here? Secant of my ID badge, tangent of my ID badge. So it's got to be secant of kx, tangent of kx. I'm done with the secant, right? Times now the derivative of kx, which is just k. And then last thing, times x. So that's that last piece right there. Yeah. You might pull something out there. What number was this? 15. Yeah, they pulled a secant kx out. Here's their answer right there. So they pulled secant kx out and it was left with this, which we could have done also, right? Here's a secant kx, here's a secant kx, pull it out, you'd be left with 1 plus tangent kx times kx. Did y'all see that? Okay, what's your other one? 33 and 13. One through 40 odd. Well, the fact that you have questions is a good thing because that means you're trying. This is number 13. Okay. So I'm going to assume here that A is a constant. X is our variable, A is a constant. I have chain rule here, right? No product. No product. So I start with the derivative of cosine of something. The derivative of cosine of something is negative sine of that something, the something being a cubed plus x cubed. Chain rule says now go inside. You've taken care of the cosine. Go inside. Can you take derivative of that pretty clean? Well, derivative of a cubed should be what? 0. 0. Right? Because it's a constant. The fact that it's cubed doesn't matter. I mean, if I say take 2 and cube it, it's 8. It's still a constant. You all see that? The derivative of a cubed is 0. The derivative of x cubed is 3x squared. Yep. So I'm going to put it in here. 0. Absolutely. Yes. What's that? A legend? Let's just put it this way. I will be sure you know what the variable is, and you'll only have one variable, so everything else will be a constant. But I will use like A, B, C, and D. I won't use K. I'll use A, B, C, and D for constants. Does that make a little more sense now? Okay. Because then you don't have to even worry about that, and that 3x squared goes out in front. So it's just negative 3x squared sine, A cubed plus x cubed. I don't like that the book doesn't really stress what the constants are. I agree with you on that, okay? Especially after what we do today, it's going to be more confusing. Okay, what else? 33? Why you got to do that to me, 33? That looks like a lot of work. Yeah. It's a good problem, though. I see division, but that division is inside of something to the fourth power. So if you were to look at like the order of operations here, the last thing happening is the fourth power. So you have chain rule, but inside that chain rule, you have the quotient, and that means you're going to have quotient rule within the chain. So let's try it out. Y prime equals, okay, we have something to the fourth power, right? All that junk in there, the big fraction. So you bring the 4 out, right? 4. Then all that junk stays there, right? I don't change it, but I raise it to the third instead of the fourth. Do you agree? Okay. Chain rule says now times the derivative of what's in there. So I think I'm going to go do some scratch work. I'm trying to find the derivative of this. 1 minus cosine 2x over 1 plus cosine 2x. And yes, that is a quotient, so I'm going to have to apply the quotient rule. I shouldn't have drawn my line like that. I need more room. The derivative is derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared, right? What is the derivative of the top? Well, derivative of 1 is 0. Then I have a minus sign. What's the derivative? Cosine 2x is a chain rule, right? It's cosine, but what's inside cosine? 2x. And you have that negative out there, right, in front of it? Okay, so what's the derivative of cosine of something? Negative sign. But the negative is going to hit the negative that's already there and become a positive sign of 2x. Now go inside and take derivative of what was in that cosine. What's the derivative of what's in there? 2. Right? Just 2. Okay. That's the derivative of the top times the bottom. So I say times the bottom, which is 1 plus cosine 2x. Now, more quotient rule, minus the derivative of the bottom. I'm writing this a little bit too small. It's okay. I'll just do this. That's equal to sine. Pardon? I hate what? I didn't say that, did I? I don't know. I may have. Well, keep in mind, though, I'm trying to be able to present everything on one piece of paper without having to go switch to new slides as much as possible. So I'm trying to put it all on one if I can. Okay, so that was our derivative. Derivative of the top time, here's right here, times the bottom minus derivative of the bottom. So derivative of 1 is 0. Derivative of cosine, chain rule again, cosine of 2x is negative sine 2x times 2. And it's negative sign, right? So I'll go ahead and put it like this. Negative sine 2x times 2. And then times 1 minus cosine 2x, that's the top, right? All of this over the bottom squared. My goodness. And that right there goes here, right? To finish off the chain rule, that goes right there. But my bet is this cleans up a little bit. Probably a lot of bit. Let's see. I'm going to clean it up. I'm going to multiply this through to here. Not the 2x, the whole darn thing. Actually, I'm going to take the 2 also. I'm going to take that whole thing and multiply it in. I get 2 sine 2x. And then when I distribute that whole thing here, I get plus 2 sine 2x cosine 2x. Yeah? Now I'm also going to notice that this negative and negative right here are going to turn into a plus, which I'm pretty happy about. And I'm going to distribute this through right here. So when I do that, I get plus 2 sine 2x. And then when I go from here to here, minus 2 sine 2x cosine 2x. All of this over the bottom squared. I'm not going to square it. No, thank you. Do you see the canceling? This cancels with this. Do you see these two can come together? Those are like terms. 2 apples plus 2 apples is 4 apples. So we have 4 sine 2x over 1 plus cosine 2x squared. What's that? Yeah, now that's just this blue part. I'm curious to see what they have. Yeah, what number was this again? It's this, right? We had this right here, right? This is 2 times 2 is 4. We have 4 sine 2x, right, over this. And then here's that part that was in the beginning. Is that what we had? We had not split it up, though, right, into 2 different things. It was all of this to the 3rd power. They just split it up into 2. And the only reason they did that is because they wanted to put this and this one together and make it to the 5th power. Right? Are we okay with that? Can I stop there then? All right. I think that's sufficient. 30 minutes of examples. Ready? We're not starting a new section yet. We will. Find equation of line tangent to y equals sine of x at the point pi 0. I just want to make sure we haven't lost sight of what we do with derivatives, right? What they mean. The derivative is the slope of the tangent line, right? Whenever we have a graph of something, we can try and find the slope of the tangent line at a certain point on that graph. So here's a graph, y equals sine of x. You've probably never seen that graph, have you? I mean, I'm sure all of you have seen sine x, but have you seen sine of sine x? Probably not. Does it make sense to have a function like that? Well, why not? Bless you. Sine x. That's what it looks like. Looks a lot like the sine function, doesn't it? It's not, though. Yeah, it looks like the phase is different, right? That's sine of sine x. And I'd like for us to go out to pi. At pi is 3.14, right? About that. At pi, we should be at 0, right? That's the point I gave you, pi 0. So at pi 0, we have an x-intercept. What's the slope of the tangent line here? Well, we need to be able to compute the derivative, right? So let's find the derivative. What is the derivative of this? Cosine of sine x times cosine x. So that's a perfect time for you to say, do I get that or not? Right? Do you get this or not? Now we want to look exactly for the slope of that tangent line at x equals pi. Right? The slope of the tangent line at x equals pi means I just want to take, right, because I'm getting the x coordinate from right here, pi. I want to take pi and plug it in right here and see what I get. So let's try it. We get cosine of sine of pi times cosine of pi. What is sine of pi? 0. What is cosine of 0? 1. So this whole part right here is 1. And then what's cosine of pi? 1. Negative 1. Negative 1. Unit circle. Cosine's the x-coordinate. Pi is over here. What's cosine of pi? It's the x-coordinate right here. Negative 1. What's sine of pi? It's this point right here, but it's the y-coordinate. 0. What's cosine of 0? Well, now you're over here. Cosine of 0 is 1. So you get negative 1. Now that just gives me the slope of the line, right? The slope of the tangent line. What did I ask for? The equation of the tangent line. So now we go back to this good old thing. Y minus y1 equals m times x minus x1. Do you know what y1 is? Did I give you a y-coordinate of the point that we're at here? 0. Equals m. Do you know the slope of the tangent line? Negative 1. Do you know the x1? Pi. And so this just turns into y equals negative x plus pi. Which means if I come over here and I say, hey, let me graph one more thing here. Graph negative x plus, I think I can just type pi and it'll do it. I should get a, yeah, that looks right, doesn't it? That looks like the line that touches tangent here and pass through that point. It looks good. I'm happy with that. I'm going to keep this up for a We say that implicit differentiation. Differentiation is the process of taking the derivative, right? That's what it means. This is a special type of differentiation called implicit. So before we begin doing it, let's make sure we understand what the heck implicit means. So I'm going to show you a comparison of what explicit and implicit, the differences between the two, all right? So what we're used to seeing, things like this, y equals x squared plus 1. This is what we call an explicit equation. It's explicit because you can determine the value of one variable, in this case y, by just knowing what x is, right? You can solve this equation for y. You can get y isolated by itself, can't you? I mean, it is already isolated, but the fact that we can isolate y makes it what we call an explicit equation. Give me x, very easy to know what y is. Compare that to this. You cannot solve that for y. I mean, you could divide through by x and you would have y here, wouldn't you? But you would also have y over here, wouldn't it still be over there? So there's no way to get y by itself, just the y by itself. The y would always still appear somewhere on the other side. Make sense what I'm saying? There's no possible algebraic way you can get the y by itself. Since you can't, we call this an implicit equation. There might be an x and a y that I could plug in to make this true, right? It might work. We might be able to. Yes, maybe. There might be a solution to this equation, some x and some y that I plug in. In fact, you know what? Let's change this real quick to sine, because then I can tell you for sure there's one. Wouldn't 0, 0 work? 0 for x, 0 for y. Wouldn't that work in there? Sine of 0 is 0, and if you plug 0 in over here, you get that. So I know 0, 0 is a solution. But there would be no easy way to get it other than trying to look and see it. See the difference between the two? When we take the derivative here, it's very clean, right? We just say the derivative of y is equal to what? The derivative of this side, which is 2x, and we're done. But what about here? Can I still talk about the derivative of y? If I can't get y by itself, is it possible? Well, remember, everything is all based on the slope of the tangent line, right? This is what the derivative means. So what I'm going to do is I'm going to come back to this program. Watch, when I hit window and I say I want to do a two-dimensional graph, right here, equation, it asks me right now, do I have the explicit form of the equation or do I have the implicit? Well, right now I have implicit. Every time I've done this so far, I've been hitting explicit. If I hit explicit, it's saying your function is what? So it's like y equals what? It assumes you've already solved for y. That's not what I have here, though. I have an implicit one. So what was it? It was sine x plus y equals y times x, or x times y. Whoa. Wow. Well, we said 0, 0 was a solution, didn't we? It is. So would it make sense that there is a tangent line there? Yes. And we would like to know what the slope of that is. But what you should notice right away about this function, or sorry, see I just screwed up. What you should know about this, the graph of this equation, is that it is not a function because it fails the vertical line test. So in previous problems, when we had something like this, when we had, okay, here's a graph, and we said we want to go out, and I wanted to go to say, let's say x equals 2, I go there and I find the slope of the tangent line, all I needed to know was the x value, and I could figure out the slope, right? Because there was only one slope at that x value. You with me? I go out to 2, I look for the graph, there's only one place that I'm going to have a tangent line. Whereas with this, if I say go to x's, let's say 1/2, then you have graph up on top and on the bottom, right? So which tangent line are you talking about? The one above or below? Well, that means that giving me just the x coordinate is not enough to be able to go find the tangent line. But we'll be able to do it. It's just having one coordinate won't generally be enough. The bigger issue is how the hell do we take the derivative, though, right? I mean, the slope of tangent line should exist. It's just how do we find it? And the way we do it is by employing what's called implicit differentiation. It's a different approach to the derivative. We will still use chain rule. We'll still use product rule. But it's just a slight little adaptation. Okay. So here it comes. Everyone understand the kind of the geometry, the picture, what's going on? All right. So let's go ahead and take that example that we are looking at right now. It was sine x plus y times xy. I would like for us to find the equation of the tangent line at the only place I really knew it existed, which was 0, 0, right? We know that that point lives on that graph. I'd like the equation of the tangent line there. So how do you take the derivative of that if you can't get the y by itself? Well, here's what you do, all right? Here's what you do. As long as I've been using implicit differentiation, as long as I've ever been doing it, I can't tell you why, but because I don't want to, I just can't tell you why. I always just drew this like wavy line to let everybody know I'm about to do implicit differentiation. I don't know. I have to, it's like I'm going to go from one line to this next line, and I'm going to do something, but I don't really have a way of saying it, so I use a wavy line. Anytime you see me do this, I'm doing implicit differentiation. So here's the way implicit differentiation works. You are going to look at this equation, you're going to look at the left side and the right side, and you're going to take the derivative on the left and the right side separately. So we'll start with the left side and we'll take a derivative. We'll go to the right side and we'll take a derivative. The difference now is that we've got x's and y's mixed together, don't we? The y used to always be on one side, and we were always doing everything in terms of x, or t, or whatever it was. So how in the world do I take the derivative of this left side of this equation? All right, well, do you see that it's composition? Do you see you have something inside of sine? Yes? Okay, so if I have something inside of sine, the derivative of that should be cosine of that something, right? So here it is. It's cosine of that something, x plus y. Chain rule then says times the derivative of what's inside. Here's where things get a little tricky. The derivative of what's inside. All right, what is the derivative of x? 1, right? Plus, what is the derivative of y? So this is where things get tricky. This is where things get tricky. We are saying that y is somehow connected to x, right? I mean, look at that graph that we had. There's x's and y's on that graph that satisfy the equation and draw your graph. Somehow, if I know where the x is, I'm going to know something about the y, right? Like if I know that my x value is, like we said, 1/2, I know something. My y would be one of two things, right? So somehow y is connected to x, or you could say y is a function of x. We just don't know what it is. Like we can't just nail it down like we normally have. But what I can say is that y is not a constant. As x changes, the y changes, doesn't it, on that graph? So y somehow needs x in order to figure out what's going on. So I don't treat it like a constant, right? Don't treat it like constant. But it's also not 1 when you take the derivative, because the rate at which y changes depends on x. But what is it that we're trying to find? I mean, aren't we trying to find... Look at this. No, I didn't go far enough. Right here. When I was at this problem right here, what was the next line? I tried to find what? The derivative. And look at the left side of the equation. What was... It's almost like we were doing implicit. We didn't realize we were, but we were doing implicit here. The derivative of y is what? Y prime, right? Now, the derivative of this was all the chain rule, but there were no y's over there, so we didn't have to consider it. So when we get to this point right here, and we're like, what's the derivative of y? It's y prime. And that's what goes there. It's the derivative of y, which is what I'm trying to figure out in the problem, right? I'm trying to find out what y prime is. Do y'all follow that? No? Yes? Let me do a few of these before you throw me out the window. Okay, have we finished the chain rule on the left side? We did cosine of something, derivative of that is, sine of something, derivative of that's cosine of something, then times, we went inside, derivative of x was 1, the derivative of y was y prime, and everyone's pissed off about that. All right, equals. Now, on the right side, it's multiplication. That means it's a product rule. You have to treat it like a product rule. What is the derivative of the first one? What's derivative of x? 1. And that hasn't changed. Times the second one. What's the second one? Y. Okay, plus, what's the derivative of the second one? Y prime times x. We're done with the product rule over here, aren't we? Okay, we're done with implicit differentiation. We just did it right here. Implicit differentiation is done. What we need to do now is isolate y prime. Get it by itself on one side of the equation. We should be able to do it. Do you see y prime right here? Do you see y prime right here? All right, the way I'm going to get the y prime by itself is I have to get it out of this parenthesis. So unfortunately, I have to distribute through with this cosine x plus y. I have no choice. So when I distribute this through, cosine x plus y times 1 is itself, and then plus y prime cosine x plus y. I just moved the y prime out front, right? Other side of the equation, y plus y prime x. I have released the y prime from the parentheses, haven't I? You might argue I've made it look uglier, but I at least don't have that trapped anymore. Now I'm going to try and get all my y primes on one side of the equation. Everything that has a y prime. So see this term right here? That term has y prime, this term has y prime. Let's move all those to one side of the equation. Anything that does not have y prime, let's take it to the other side. And you'll see what will happen. Do you agree? See what happened? Y prime x came to the left, which means it made it negative. Cosine x plus y went to the right, which means it made it negative. Why do you think I've done all that? That's right. I can actually factor a y prime out of this now. Right? This is y prime times this minus y prime times x. Factor a y prime out. If that y prime is now factored out, and that's what I was trying to solve for, right? I can come and get rid of this by dividing it on both sides. So y prime equals y minus cosine x plus y over cosine x plus y minus x. That's your derivative. That is the derivative. I want you to notice something, though. It's very important here. When I was saying look at this picture, I said if you go to like x is 1/2 and look for the slope of the tangent line, I said there's 2 points, right? Like if I just told you x is 1/2 and said what's the slope of the tangent line, you wouldn't know where to go, right? Up or down? You wouldn't know? You would have to give me both the x and the y, wouldn't you? Like that point right there, you would have to know the exact coordinates, the x and the y coordinates for you to be able to talk about that as opposed to down here. Well, look at our answer for our derivative. What does our derivative require in order for us to compute? X and y, right? So having just x is not enough anymore when you're dealing with these implicit equations. You have to have that point nailed down exactly. Now, I actually do in this problem, don't I? 0, 0. So let's go finish this off, because remember I wanted the equation of tangent line? So let's find the slope. The slope of the tangent line at, notice I'm going to put 0, 0. So what is it? What's our slope? Plug in 0 for y, 0 here. So what is cosine of 0? 1 and then minus, so -1, and this was 0. So we get -1 on top. On the bottom, cosine of 0 is 1 and then minus 0, so 1, so you get -1. That's your slope. Now we go to the y minus y1 equals m times x minus x1. So y1 was what? 0, so that's why I put y here. X1 was 0, so that's just going to be x. What's my slope? -1, so -x. Y equals -x is the equation of the tangent line. Questions? I'll just draw the other one real quick. It was -x. There it is. Right through there. I'm not sure what, I'm just getting this vibe from you all right now. Are you all okay? Recall some notation. Do you remember y prime we said we had that other notation, dy dx? Remember that? It's called Leibniz notation. And I said a long time ago that Newton was kind of like, when it came to, who is the man when it came to calculus, like Newton was considered to be the man because his calculus was more powerful than Leibniz. But Leibniz's notation was in some ways better than Newton's, and so, in certain places. And this is one of those places where Leibniz notation is actually more useful to us. So what I'd like to do is I'd like to put the same problem on the board. I'd like to do the implicit differentiation, but I'd like to show you it with Leibniz notation, and then from here on out, when I do implicit differentiation, you know what I'm saying, implicit differentiation, I will use Leibniz from here on out. You'll see why when we get to related rate problems. Okay, so let's put that problem back up here. Sine x plus y equals xy. Find dy dx. Let me point out a few things about this notation that makes it more useful. When you have dy dx like this, x is what we refer to as the independent variable. And that tells you right here, the x on the bottom tells you that whenever you take the derivative of x, it's 1, okay? But when you take the derivative of y, since the y is on the top, the derivative of y will be y prime. Does that make sense? But with using this notation, the top is the dependent variable, the bottom is the independent variable. The derivative of the dependent variable is never 1. The derivative of the independent variable is always 1. Yes? So when we go back through this, and we come through and we do our implicit differentiation, the derivative of sine of something was cosine of it. Chain rule says, then take derivative of what's inside. What is the derivative of x? In this case, it's 1. Right? It's 1. So I put 1 here, plus, now what's the derivative of y? Y prime, but I'm using Leibniz notation now, so I'm going to write dy dx. That's the derivative of the left side. Equals, derivative of the right side was product rule. 1 times y plus dy dx times x. All I'm basically doing is replacing y primes with dy dx, right? Yeah. But I don't want you to think of it as being like why is he making it more complicated? Why doesn't he just say switch the y primes to dy dx? Because it's what I want you to realize about what's happening in here with the notation. In fact, if you look at it that way, when you get right here and you were taking the derivative of that and you got 1, the reason why was because you were taking the derivative of what? X with respect to what variable? What's the bottom? According to Leibniz, if we're trying to find this, we're treating x as the independent variable, so that's going to be down here. This right here means take the derivative of, well, what is that, x? That's x right there. So this right here is this. I'm taking the derivative of x with respect to x. So dx over dx should be 1. But when I get here and I say, what's the derivative of y with respect to x? Well, that's what I want to know. What is the derivative of y with respect to x? That's what I'm trying to figure out. I don't want to put the carriage in front of the horse here, all right? But the reason why it's so important that you understand that concept is because in a section or two, no, next section, sorry, which is the hardest section in the entire semester, I think, from my opinion on Calculus 1 students, because it's word problems, all right? But in this section, we're going to have equations that have several variables, not just x and y. We're going to have multiple variables. And we're going to be differentiating with respect, not to respect to x, but with respect to time. So if we differentiate with respect to time, we need to know how to treat every little variable when we get to it and try and differentiate it. Some of them turn to 1, some of them don't. All right, I did get the carriage in front of the horse. All right, that's all. I'm done. There's the derivative. We would move on. We would try and isolate dy dx. Same thing, we distribute through. We just treat this right here like y prime the whole time. Just bring it along and move it around. But I think you need some more practice with differentiation. So here we go. Find dy dx for this implicit equation. X cubed y minus 4x squared y to the 4th equals x plus y cubed. Now, I don't think anyone in here would want to try and solve that equation for y, right? That does not look fun. However, there is a possibility that you can still get the derivative and find, slopes of tangent lines and things like that if you can find this derivative implicitly. So let's do it. Here it comes. Because I've asked for dy dx, anytime you get to x, the derivative would be 1, right? Anytime we get to y, it would be, well, dy dx, right? But we still have to pay attention to all the rules. Product rule, quotient rule, chain rule, all has to be, power rule, all has to still be in play. So let's move across this thing, left to right. Derivative here, what do we have? Product rule, right? See my product rule right there? Okay, derivative of x cubed, 3x squared. So 3x squared times y. That's the beginning of the product rule. Then I say plus, now the derivative of y. What's the derivative of y? Dy dx. Times, finish off the product rule, x cubed. Okay, that was just the derivative of this piece. Got it? Just this. Next, this. How are you going to deal with that minus 4? Do you want to just bring it out as like minus 4 and then deal with product rule on these two right here? Okay, then if I'm going to do that, I'm going to need to leave that minus 4 out front and do my product rule in there. Understand what I'm doing? Here's my product, right between the x squared and the y to the 4th. Product rule. Derivative of x squared is 2x times y to the 4th, right? Plus, now, it's the first time we've faced this. It's so subtle, but it's so important that you understand what's going on here. Bring it down here. Let me back up for a second. X squared. When we took the derivative of x squared, everyone was like 2x, and it's like you don't even think about it anymore too much, right? You don't? But really, this is what happened when we said x squared, and we took the derivative. That's too high. I can't get to it. When we said x squared and we took the derivative, we actually did the chain rule. Here's what we did. We covered up the x, and we said, what's derivative of x of my hand squared? 2 times my hand, right? Then chain rule says, now take derivative of your hand. What's derivative of my hand? 1. So it just turned out to be 2x, didn't it? Yes? But that's not what's going to happen for this one. I mean, it's the same thing over there, but watch. That's chain rule. What's the derivative of my hand to the fourth power? 4 times my hand. My hand is y, isn't it? To the third power. Now, uncover my hand. What's the derivative of y? dy dx, or y prime. Then times the what? X squared. This is the part that gets most students right there. That's the one. That's the little thing in implicit differentiation. Students lose the. I don't know. Like they'll put 4y cubed, but they'll forget the dy dx. Do y'all see it though? Y to the fourth is your hand to the fourth. 4 comes out. Y cubed. Now the derivative of y is y prime, or dy dx. All right, let's see. We're not done, right? Are we done on the left side? Yes. Equal sign now. Okay, now we have x plus y cubed. So I can do these separately. What's the derivative of x? This time it's 1. Or, if you like, you say it's dx dx, but that's 1. And then we have plus. Now what's derivative of y cubed? 3y squared times dy dx. Chain rule, baby. Chain rule. That's what it is. Y cubed, derivative of y cubed, 3y squared, dy dx. Make sense or not? It's going to take some practice to not miss it. You know, to get it every time, that's going to take practice. Now, you would have to isolate dy dx. So you would have to get this. It appears in 3 different places. So I would have to distribute my 4 through, and then I'd get all my dy dx's to one side, everything that doesn't have dy dx to the other side, and then factor out a dy dx and divide through. It'd be a mess, but it could be done, and that's not something I'm willing to show. So I just say, you know, like dot, 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 dot. Because at that point, it's just algebraic manipulation of moving things around. That would be your ending of taking the derivative, and then the beginning of algebra to move things around. That's right, yeah. I'm not done. That's what the dot, dot, dot means, though. You could go find dy dx now. Look, look, look. Like I did on this, well, no, not this one. I know you're not happy with that answer. But like I did here, remember I distributed this through, moved all the y prime stuff to one side, factored it out, divided through? It's exactly what you would have to do to finish this problem. I know you want me to do it. I'd be happy to do it in my office after class, no problems. You would have to then continue to go through the problem, yes. Yep. I understand it's not the most beautiful thing to look at, but right now I'm just trying to get you comfortable with taking the derivative implicitly. That's really the key to it. The getting the algebra part of it will come when you do your homework. And you won't like it, but it'll... Well, that doesn't look fun, but let's do it. How about this one? Tangent x squared over y equals 1 plus the square root of xy. Those don't sound like sighs of relief. Those sound like sighs of, I don't know, the opposite of relief, whatever that is. We have a lot going on in this problem right here. What is, let's find, first let me tell you what we need to find. We're going to find dy dx. Do you like the y prime better? If you do, that's okay. You just better remember that y prime means dy dx, because it can get you in trouble later if you're not keeping that in mind, all right? But if it's easier for you to work through the algebra of it by writing y prime instead, that's fine. Okay. Left side. I'm coming through. Here we come. Implicit differentiation. What is the derivative of tangent of something? Secant squared of that something. Chain rule, right? Times the derivative of what's in there, which is which rule? Quotient rule. So I'm gonna get the quotient rule set up here because I kind of know the way quotient rule looks. Might need a bigger division bar, I don't know. It should be the derivative of the top times the bottom minus derivative of the bottom times the top, all over the bottom squared, yes? What is the derivative of the top? 2x, and I'm happy with just 2x, right? 2x times y. Now minus the derivative of the bottom, which is dy dx, or y prime, times the top, x squared. Man, I don't like that. dy dx times x squared, all divided by y squared. Are we done on the left side? Yes, we've done the chain rule. We've got secant squared out there. We've got times, and we've got the quotient rule. Left side's done. Equals derivative of right side. Derivative of 1 is 0, so that's gone. Derivative of the square root of something is 1 over 2 root xy. That's what the derivative of the square root of something is. Then times the derivative of what was in there, which is what in here? What is happening here? What is that? Product rule. That's a product, isn't it? X times y. That's x times y. So you have to do product rule now. Y'all are looking at me like this is my fault. You know, I understand that, but I mean, calculus has been around for a long time. I'm not sitting here like in my office coming up with like, I'm just going to make up this math that's just going to be all crazy. I mean, this is the way calculus is. I mean, you just got to get used to it. It's weird, but you got to get used to it. I'm the messenger, trying to communicate it as best I can, but the message is the message. What the hell? What's the product rule here? Derivative of x, which is 1 times y, then plus or y prime times x. I think it's obvious to you how much room there is for error, right? Just there's so many little subtleties that, if you forget this dy dx here, it's completely wrong. I mean, yes, you did a lot of the derivative right, but if you ever needed that derivative to build a bridge, the bridge is coming down, So there's a lot of room for error. I would not take off, like out of 10 points, if you forgot that, I would take off maybe 9.5. No, I'm just kidding. I would take off a few points, maybe, 1 or 2 or 3. No. No. Why wouldn't I give you the answer? Well, that's a great question, but if you were to look at this answer, if you were to look at an answer, you could actually reverse engineer the steps. From the answer, you could actually see, oh yeah, I needed the quotient rule. That's the only way that was going to work, is if it was quotient. Oh yeah, that's quotient. So, well, let me ask you another question. Let me ask you another question then. Let me answer your question with a question. So in the real world, if there is a problem that needs to be solved, then how often are you going to be supplied the answer and just asked to get to that answer? Part of the challenge of the course is being able to actually get to that answer without... Yeah, but when would you ever be told to do something that's already been done? Like, look, look. When it comes down to this, right, if it's a matter of taking a derivative, there's going to be someone out there that can take a derivative and can do this all the way and will have no problems with it. The question is, can you get yourself to that point? And a lot of people in here, your major is not math. Your major is something, biology or, something else, right? So you're sitting there going, what in the hell do I need this for, right? It's a process. It's a level of thinking. It's a level of thinking. That's what it is. And so what they're doing is they're weeding out people who cannot achieve a certain level of thinking. That's why when I first started teaching, pre-cal was the requirement, the maximum requirement for med school, pre-cal. It's Cal 1 now for most med schools, and I'm hearing that it's going to Cal 2. Why? There's too many people who want to be doctors or whatever. So you have to find ways to weed out. I don't know if I'm getting to your point, but I'm sorry, but I understand your frustration, but please understand that it's my job to make sure everyone achieves a certain level of thought process. I'm done. I'm not going to take this the rest of the way. But it would be nasty. You'd split this into two fractions, this over this, this over this. Then you would distribute the secant thing through it. Then you would distribute this through here. And then you get all your dy dx terms on one side, everything that doesn't have it on the other side, factor out, divide through. It'd be really ugly. But we have a derivative. We would have a way of finding the dy dx, the instantaneous rate of change. And that's what we want. You'll have one of these. You'll have one of these. I don't think it'll be like this. Do your homework. I think if you do your homework, you'll get an idea of what I'm looking for. Yeah. What I'm trying to give you right now are problems that have enough complication in them that you understand the derivative process. I mean, I gave you something where you had chain rule with quotient. Over here, more chain with product. As far as the simplification, well, that's busy work. Yeah. Yeah. But don't we have a holiday the Wednesday after that? No, not Columbus Day. October 29th. Never mind, that's too far away. Hey, look, there's no sense in sitting here. Why don't you do a problem? Okay? This is number 4 out of the book, out of this section. Yes. We're supposed to have a test next week on Wednesday. Next Wednesday. So what is the issue? What is the problem? Because I'm sensing a major pushback here. What is the issue with this? I mean, you need to tell me what it is that's causing the problem. Is it the part at the end where you have to solve for the dy dx that you're concerned about, or is it the derivative itself? The algebra stuff at the end? Okay. Okay. So that's the part that you're most concerned about? Okay. Well, I would say don't worry about that right now, okay? Because what you need to be able to do is take derivative, because if you can't take derivative, the algebra after that doesn't matter, right? So just work on the derivative, and the thing is you won't be able to check your answer in the back of the book. You won't know if your derivative's right, because they're going to solve for y prime, and so how do you check? Right? You know what I'm saying? Trying to think if the book will show the derivative worked the way. I can look at it. Yeah, I might just pull a copy of those pages or something. Do this one though right now. Just the derivative. Don't worry about getting and solving for y prime. Just the derivative. I don't know. I just stand up here and act like I know what I'm talking about. Ask one of your classmates. I think you're right. I don't know. Derivative 2 is 0? I don't know. It's a constant, right? That never changes. That's never going to change. I'm never going to say, Ed, remember when constant's the derivative? I'm never going to change that. It's always 0. Just take the derivative. If you get an answer, just raise your hand so I know you got there. Okay. Just kind of wait a few more minutes. Mm-hmm. Did you pull the negative out and do the product rule separate, or? Yeah, right here and did product there. That's fine. The answer's up here. Does yours look close to that? Close? Where? Yeah, did you put your negative and then put like a bracket or parenthesis and do the product rule? Okay, be careful with that. That negative would have to be distributed. Yeah, it'll change. That's the part of the problem I think is a little tricky on this one, is that minus right here. I passed it through after. I mean, I kept it out. Mentally, I did the product rule, but then I passed the negative through after. That's right. If you would have left this positive, you would have needed this to be like this, or parentheses. That would have been okay also. Okay, we got about 10 more minutes. I've got a few more things I want to show you with this. Let's say we have square root of x plus the square root of y equals 1. You have to find y double prime. You have to find the derivative and then again the derivative. But the derivative of the derivative, so second derivative. First thing I'm going to do is look at this and say, look, I have an equation. I could just take the derivative right now, right? Implicit differentiation straight across. That's my choice, but before I do it, I'm going to rewrite it so that, well, no, because you know what the derivative of the square root of something is, right? Okay, so let's do it. Derivative of the square root of x is 1 over 2 square root of x, bless you, plus, drum roll, derivative of the square root of y is 1 over 2 root y times dy dx or y prime, right? See, on this one, let's put my little mouse there. What's the derivative of the square root of my mouse? 1 over 2 times the square root of my mouse. There it is. Now, the derivative of my mouse was the derivative of y, which is y prime, or dy dx. In this particular problem, I think I'll put y prime, only because I'm going to need y double prime. So just to keep my notation a little cleaner, I'm going to put it here. That wasn't product rule, right? That was just straight up derivative of this, equals 0. Now, you might be thinking, okay, well, you might be thinking, yeah, that's why I said in the very beginning, I said I was going to rewrite it, but I said no, but y'all know what the derivative of square root of x is, right? So I need the derivative again, right? If I want to do the derivative again, I can do implicit differentiation again. That's perfectly fine. But if I'm going to do it, I might want to rewrite it before I take derivative. How about this? Is that the same equation? I have not taken derivatives or anything. Is that the same? 1 over 2 square root of x is the same as this. 1 over 2 square root of y is the same as this. And then our y prime is back here. What you were saying is if you would have started off the problem by switching this to x to the 1/2, y to the 1/2, you would be here now, right? Yeah, you would. Is this okay? I'm ready to take a derivative again. And here I come. What is the derivative of 1/2 x to the negative 1/2? So if this negative 1/2 comes out, power rule, negative 1/4 x to the 3/2 plus product rule right here. The derivative of 1/2 y to the negative 1/2 is negative 1/4 y to the negative 3/2. Do you all agree that's a derivative of this? Times y prime. More product rule plus the derivative of y prime. Y prime prime, which is y double prime. Isn't that what we're trying to find? The derivative of the derivative should be that. Finish off the product rule times this. And then there's cleaning up to do there, but we're running out of time. We need to talk about this test. Take a look at something real quick. Exponential log, all right. Here's my advice to you. We are supposed to have a test a week from today? No. Yes? A week from today. Which would only cover, which was supposed to cover up through 2.7, right? 2.7 is the most difficult section that you will have seen. Because like I said, it's applying all this now to word problems. So my recommendation is this. We come in here on Monday, and we review for the exam. We talk about the exam that we will have on Wednesday of next week without 2.7 on that exam. But this is on the exam, all right? And that will make your next exam have quite a bit of material on it. But 2.7 won't be there, which is good. Because I don't think I can treat 2.7 properly in one day. There's just no way. So I will work on, I have another class having a test next week. My Cal 3 right before this is having their test on Monday. So I'm going to be making their test. And then what I'm going to do is work on a review for you. And my plan will be in the next 24 to 48 hours to email a review or post it on our class website, problems for you to go look at to prepare for the test. It's going to be, your test will cover everything from 2.1 to 2.6. This is 2.6. Yeah, homework you should look at page 127. Three through 15. Odds. Try number 25. I hope what this comes down to for you is the algebra is the problem. You know, well, I'm not hoping that problem on you, but I'm just saying that I hope you're okay with the derivative part of it, because in the big picture, that's the part you've got to get good with, is the derivative. The algebra, though, you need to practice. You need to work on it. You really have to. I mean, I told you in the very beginning of the semester, calculus is algebra on steroids. It is. It's the algebra never stops here. All right. Have a good weekend.